Today, we are diving into this really fascinating paper that explores a super weird consequence of Einstein's most famous equation. It's an idea that sounds like it's straight out of science fiction, and it totally challenges something we all just assume is true about the world. So let's just get right to it. Here's the big question. Can you make something heavier just by spinning it? Without adding a single atom to it. Is that even possible?
Well, it sounds completely impossible, right? But believe it or not, according to physics, the answer is yes. Yeah, you heard that right. So how on earth does that work? Let's unpack this.
Okay, to really get how motion can add mass, we've got to connect two really big ideas from physics. These are basically the foundation for this whole thing.
First up, kinetic energy. You've probably heard of this one. It's just the energy an object has because it's moving. Simple. The faster you spin something, the more kinetic energy it has. That's piece number one of our puzzle.
And here's the second piece, and this is the real game changer: mass-energy equivalence. This is the mind-blowing idea that mass and energy aren't really separate things. They're just different forms of the same thing, two sides of the same cosmic coin, really. And of course, this is the equation that ties them together. But here's the part people sometimes miss. E equals m squared isn't a one-way street. It's not just that mass can become energy. It also means that energy, all by itself, actually has mass. So that kinetic energy from our spinning object, Einstein's telling us that energy has inertia. It has weight.
So if the energy of motion has mass, how in the world would you even calculate that? Well, the paper we're looking at uses this brilliant little thought experiment. It simplifies the whole problem down to a perfect, idealized model so we can see the effect without any other noise.
So here's the setup. You imagine a cylinder, and you fill it with what's called a perfect fluid. Now that just means you can't squish it, and it has zero friction. It's perfectly smooth. Then you spin the whole thing up at a steady speed. This perfect little model lets them get rid of all the messy real-world stuff and just calculate the numbers cleanly.
Now, inside this spinning cylinder, the kinetic energy is different depending on where you look. Right at the center, the fluid is barely moving, so its kinetic energy is basically zero. But out at the edge, that's where the fluid is moving the fastest, so its kinetic energy is at a maximum. And that little detail is absolutely crucial. And this is where it gets so cool. The paper takes that spread of energy, applies E equals mc squared, and boils it all down to one single beautiful formula. A formula that tells us exactly how much effective mass is being created just from the spinning motion. Which leads to the obvious question, right? How much heavier does it actually get?
And here it is. This is the answer. Now, I know it looks a little scary, but trust me, it's telling a really simple story. Let's just walk through what each part means.
So on the left, that's just the fractional increase in mass. You can think of it as the percentage of new mass we just created. On the right, the edge is the speed of the fluid right at the outer wall. And c, well, that's the speed of light, which is a ridiculously huge number. The 1/4 is just a little factor that has to do with the cylinder shape. So what this all means is the new mass depends entirely on how fast that edge is moving compared to the speed of light.
All right, so we've got the theory, we've got the formula. Now let's have some fun and plug in some numbers to see what this really looks like. The paper gives us two scenarios at completely opposite ends of the scale, one in a lab and one way out in space.
So we're going to compare a cylinder of water spinning really fast here on Earth to a rapidly spinning neutron star, one of the most extreme things in the entire universe. This comparison is just going to show you the insane scale of this effect.
Okay, so for the cylinder of water, spinning at about 100 meters per second at the edge, the fractional mass increases this, 3 times 10 to the negative 14. That's a 0, a decimal point, and 13 more zeros before you even get to the 3. It is an absurdly, impossibly small amount, totally undetectable.
But now, look at the neutron star. It's spinning so fast, its edge is moving at 10% the speed of light. Its mass increases by about 1/4%. Now that might not sound like a lot, but for an object that's already heavier than our sun, adding 1/4% is like adding the entire mass of a planet, out of nothing but pure motion. That's a universe-altering amount of mass with a real gravitational pull. And this quote from the paper's author, O. Iskandarani, really says it all. The reason we never, ever notice this is because the effect is just many orders of magnitude below what we can even measure.
You really need cosmic-level speeds for it to matter. So let's just take a step back and think about what we've just seen. This pretty simple thought experiment has shown us something truly profound about how mass, energy, and motion all connect.
So what are the big takeaways here? Well, first, that all motion has mass. That kinetic energy isn't just some abstract number, it has a real physical presence. And this isn't just a weird theory, it's a direct, tangible consequence of E equals mc squared, happening all around us. But crucially, the effect is basically nothing at everyday speeds, but becomes a massive, cosmic force when you get close to the speed of light.
So the next time you see a wheel spinning, a planet turning, or you're just, stirring your coffee, just remember what's actually happening. You're literally watching pure energy turn into a tiny, hidden bit of extra mass.
And that really leaves us with one last thought to chew on. If something as simple and everyday as motion has this hidden property of mass, what other bizarre, fundamental realities are still out there, just waiting to be discovered right under our noses?